In a combustion reaction, understand that there are a basic definition for a combustion reaction. So a combustion reaction is when a substance reacts with molecular oxygen. Okay? Remember that molecular oxygen is O2. By definition, that is a combustion reaction. Now, understand that there's a very specific parameter when it comes to combustion reactions. If the substance reacting with molecular oxygen contains carbon and hydrogen, or carbon, hydrogen, and oxygen, then the products will always be CO2, water, and energy. So as you can see here, whenever you have a gas stove and you're turning it on, that gas that is coming through the line contains carbon and hydrogen. And here we are just illustrating it when you have methane gas. Now, when we expose it to the O2 that is in the air, and then, of course, you have to create a spark to get it initiated, then that carbon and hydrogen and molecular oxygen gets converted into carbon dioxide gas, water gas, and energy. And in the energy in this instance, we see it in the form of the flame. Table 7.5 in the textbook summarizes the different types of reactions that you guys have to be familiar with. Now, understand that there is one more parameter that we're going to discuss later, but for now, let's just practice on the classification of these reactions. Okay? So, I'm going to just do the top 4 to just visualize the examples. So as you can see here, nickel took the place of the hydrogen and hydrogen got displaced or replaced. So this is a single replacement reaction. In the second reaction, we have one substance converted into multiple. So this is a decomposition reaction. On the second one, you can classify it as a combination because we have nitrogen and oxygen forming dinitrogen pentoxide, or you can define it as a combustion reaction, because remember that by definition, a combustion reaction is going to combine a substance with molecular oxygen. In the last one, as you can see, we have two aqueous components, and then if we break them into ions, this is K plus, OH minus, this is H plus, and this is CO3, 2 negative. These ions are going to exchange, and then the cation of the first is going to combine with the anion of the second, and then the anion combines with this cation. That's where the water comes from. And this is where the potassium carbonate comes from. So that's why this reaction is a double replacement reaction. Now, the next set of reactions that we're going to talk about is oxidation reduction reactions. And when it comes to oxidation reduction reactions, understand that these are not a brand new set of reactions. Oxidation reduction reactions are present or are part of in combination reactions, decomposition reactions, and single replacement reactions. Now, when it comes to oxidation reduction reactions, understand that these reactions are very important because they provide us with energy from food. They even provide the electrical energy in batteries. So to illustrate an oxidation reduction reaction, you can see here iron rusting. So when we have the combustion reaction or combination reaction of iron reacting with molecular oxygen, making iron 3 oxide, that's an example of an oxidation reduction reaction. Let's look at them more closely. When it comes to an oxidation reduction reaction, understand that the basic idea is that electrons are going to transfer from one substance to another. So the substance that transfer the electrons, that's the one that gets oxidized. The one that receives the electrons is the one that it gets reduced. So understand that this transfer of electrons happens at the level of reactants So that's where we see the transfer. We don't see the transfer of electrons at the product side. Now, there are some mnemonics that are utilized in order for us to remember what is oxidation and what is reduction. And I'm just giving you here in the bottom one of them, oil rig. Oil is because oxidation is loss of electrons. Rig stands for reduction is gain of electrons. Okay. Now, in order for us to determine specifically what is getting oxidized, what is getting reduced, we should remember the rules for oxidation numbers. In these rules, there's 3 basic rules, and this is what's going to help you to determine, okay, what gets oxidized and what gets reduced. Rule number 1, any element found in elemental form has an oxidation number of 0. So for example, if you have a diatomic molecule, has an oxidation number of 0. If you have an element that happens to be a metal and you see it in the reactant in metal form, or in solid form, I should say, that is going to have an oxidation number of 0. Now, the second rule is in ionic compounds, the charge of the ion is the value for its oxidation number. So understand that it's not going to be numerical, because if it's negative, then you retain the charge. You retain that negative value, okay? And lastly, covalent compounds is going to be a little bit more complex. In covalent compounds, there's several rules that we need to take into account, okay? Remember, covalent compounds share electrons. We do not have ions forming. So, in covalent compounds, this is the way that we visualize them. In covalent compounds, the charge, okay? So I put in quote charge because in covalent compounds, those nonmetals do not have charge. That's why I'm just mentioning it. In covalent compounds, the charge of the second nonmetal equals its oxidation number. Then the oxidation number of the first nonmetal when added to the total value for oxidation of second nonmetal must equal 0, unless we're talking about a polyatomic ion, then it's going to equal the overall charge of the polyatomic ion, okay? Or charge value. So I just want to specify that. Now, let's look at an example to apply these rules. Here we have the example of what is occurring at the Statue of Liberty. So one of the things is that the Statue of Liberty was not always green. The reason why it's green is because the copper metal that the Statue of Liberty is made out of has undergone an oxidation reaction. Okay, so as you can see here, when we look overall, even though the overall result is already written on the slide, let's actually rationalize it. So when it comes to determining the oxidation number for everything that is in the reaction, remember copper is solid, it is a metal, is going to have oxidation number of 0, just like the first rule establishes, because it is in elemental form. Oxygen is a diatomic molecule, is also found as elemental form, so it's going to have an oxidation number of 0. So the values that I'm writing in red is going to be the oxidation numbers of it. So CuO is an ionic compound. So as I established, because it is an ionic compound, the charges of each of those is going to be overall their oxidation number. So that means that the copper oxidation number is going to be 2 plus the one in oxygen is 2 negative. So whenever we're comparing what is occurring to these molecules, understand that we're going to go from what happened in the reactant and how does it look in the product. So as you can see, copper went from 0 to positive 2. Oxygen went from 0 to negative 2. Okay? So because copper went from 0 to plus 2, that means that it lost 2 electrons. So it got oxidized. Oxygen received those 2 electrons. That's why it became negative. So that is reduction. Another way that I like to visualize how to determine if something is undergoing oxidation and reduction is utilizing a number line, in which we have 0, we have the negative values on the left of 0, the positive values on the right of 0. So as things get lower in number towards 0, past 0 into the negative, that means reduction is occurring. And when things are going from negative towards 0, past 0 into the positive, then that means that oxidation is occurring. Let's look at some examples from the worksheet. So this is part H on the worksheet, okay? So when we look at these oxidation reactions, let's first determine the oxidation numbers for these elements. Magnesium is in its elemental form, so it has an oxidation number of 0. Now, HCl can be broken into ions. So remember, Cl is -1. This is a covalent compound. And H is going to be specifically going to be +1. Because remember, overall, this doesn't have a charge. So when we add those oxidation numbers, -1 plus +1, that must equal 0. Remember, HCl is a covalent compound. Then magnesium chloride is going to be an ionic compound. So we're going to reassign the charges, which is going to be their oxidation numbers. So magnesium is +2, chlorine is -1. And then our hydrogen, because it's an elemental form, it has an oxidation number of 0. So when I make my list, I'm just going to put it up here. In the reactant, or I should say, I'm just going to write the change of oxidation numbers for each of the elements. I have magnesium, I have hydrogen, I have chlorine. So magnesium went from 0 to +2. Hydrogen went from +1 to 0. And chlorine went from -1 to -1. So that means that chlorine specifically, because there wasn't any change in the oxidation number, this is known as an spectator ion. Because it was present in the reaction, but it didn't have any gain or loss of electrons. So when we look at these, we should note that because magnesium went into more positive, let me just rewrite my number line. So magnesium went from 0 to positive, okay? If you're going in that direction, that means that you're getting oxidized or you're undergoing oxidation. In the case of hydrogen, it went from positive and it went towards 0. That means that it was undergoing reduction. So in this case, we're going to say hydrogen got reduced. I'm going to do problem number 2. Let me utilize a different color. Chlorine is an elemental form, oxidation number of 0. Sodium bromide is an ionic compound. The charge of sodium is going to be its oxidation number, so it's going to be +1. Bromine, it has a charge of -1, so that is also its oxidation number. In the product side, we have sodium at +1, chlorine at -1, Br2 is an elemental form, so it has an oxidation number of 0. So when I write Cl, Na, and Br, Cl went from 0 to -1. Sodium went from +1 to +1. Bromine went from -1 to 0. So that means that sodium is our spectator ion. And in this case, chlorine, because it went into the negative, it got reduced, or it was undergoing reduction. Bromine, because it went from from -1 towards 0, so bromine, because it went from -1 towards 0, it got oxidized. And this is how you do problems in terms of determining which element got oxidized and which one got reduced.